There we go. Okay, so if anyone wants to attend, it should be live, and we will first go to some slides or some Scala interactive session, and later we're going to go and go through some slides that will set us up for this next little phase of the course, which is going to be dealing with this important construct of monads that we have been dealing with kind of informally in various ways with collections, streams, try, either various quantities such as that option. And we're going to unite a discussion of them with in the topic of monads. Per chapter 6 in the book. That's coming. We're probably just going to get a glimpse of that today. But first, we're going to, as the title indicated, have some fun with streams. Okay? So I decree the beginning now of the fun. Okay. So I'm going to call up the Scala shell. And I'm going to explore within the coming minutes, and it'll probably last a fair fraction of the class, the exercise that I asked you to follow for today's class. This is take-home exercise 5 here. And take-home exercise 5 is composed of 3 subparts. Each of them reflects use of streams, and they build on some topics that we've explored in recent sessions, including the use of co-recursive procedures to produce streams. In the first of them, I asked to create a function or a method, as you see fit, to return a stream where the successive elements of that stream are the successive factorial numbers. So 1, so that's 1 factorial, and then 2 factorial, and then 6, 3 factorial, etc. Where each factorial is defined, the factorial of n is defined as n times n minus 1 times n minus 2, all the way down till 1. Okay. And I asked you to define a factorial stream. Does anyone want to advance an idea of how you could define such a factorial stream? How might you approach this? So I'll say def factorial stream. Oh, I'm pausing here. Pausing as to what? Why might I be pausing at this point? Well, we can't explain that delay by. We can't explain that non-response by a delay anymore. So,
we have to decide what arguments to put.
Yeah, we have to decide what arguments to put. Yeah. And what's particularly notable is that when we have these co-recursive sort of types of functions, where we have a function that's used to produce a stream, the arguments to that function are used to maintain state of sorts that's used to figure out what the next stream element is. And so the choice of arguments is in many ways central to how this is going to work. It's the choice of once you've decided what your arguments are, the rest will sort of fall out of it. Okay, it will sort of follow systematically from that. So the choice of arguments, even more so than the choice of body, is sort of fundamental here. What's one way that we might define a function? What might it take as an argument? Good. Excellent. Excellent. That's what I was exactly what I was going to suggest as a first definition. As we'll see, I'll be providing several alternative definition or another alternative definition. So one might be sort of something like the current factor. I'll call it factor because we multiply by it. Okay, so I'll call it a current factor. And then maybe I'll say last fact. So this is n minus 1 factorial. And that will be a long as well. So here it's maintaining these two aspects of state. So if you tell it the current factor and factorial of n minus, so this is basically n. The first thing is n, and the last thing is factorial of n minus 1. So perhaps you have an even better way of naming them. This is going to return a stream, not a string, a stream of longs. Oops, long. What's the first element of that stream going to be? Given what we've got as arguments, what's the last element going to be, or the first element going to be? Sorry? Yeah, current factor times last fact, right? So if this guy is factorial of n minus 1, multiplying by n is factorial of n. Okay, great. And then what do we got to do? Is that all? No, what do you have to do? Yeah, I love it. I love it. It warms my heart on a cold day. I hear cons, and I'm a happy camper. Okay, so so we cons it onto it. We sort of append it onto this, and so we have to append it to what? Factor plus 1. Okay, yeah. So this is one way to do it. And there's some common sub-expressions here. You'll notice this guy occurs twice, right? Which, you know, okay, what did I not do? Not found. Last fact. Oh, I called last factor. Okay, last fact. Last fact, not factor. There we go. Boom. Okay. And now let's produce some factorials. Factorial stream. Okay. And let's give it 1, and the last fact we'll say is 1. And let's take 5 of them and let's force them. What is taking 5? What does this one do? Yeah, it requests the first 5. So it's they're a stream of just 5. I'll show it to you. This is just a stream of 5. But still, only the first is evaluated. By forcing them, we can get them all to be evaluated. And there they are in their fulsomeness and even glory. Right? Okay. So that will work. That will work not badly. Now, the software engineer in me says, look, this means something. When you see common sub-expressions, when you see repeated expressions occurring again and again, there's typically some concept, some latent concept, some hidden concept there. And indeed, this means something. I mean, the reason it occurs twice is because it's fact of n, right? So of the current value. So part of me says, well, that's all well and good from a nice, crisp mathematical standpoint. But what I'm going to do is I am going to actually say here, val, fact of n equals current factor minus last fact. Or maybe I'll say, current fact, right, equals this guy. And then all I have to do to return the current value is to append him onto or her onto this the same basic mechanism here. So I'll go boom, and then I will go bang, and I'll put current fact. There we go, current fact, and put them on. And what goes here, where my cursor is? Current fact. Current fact. Cool. So I would say the intentions here are a little bit clearer, because for someone looking at this, they could see, oh, that's the current factorial value, and we're appending it to, we'll call it the factorial stream, where the current factorial is passed as the last fact, and we're just keeping track, of the current factor. Probably be clear if this were called n and this were called, fact of n minus 1 or something. So this is another way to define it, which I would argue has a little bit more clear intentions behind it. People comfortable with that? Okay, but now I'd like to, by the way, if you have this in Scala, the last one is the one returned, right? It's kind of like R in that regard, for those who know R. Last one is returned. Okay, here's another way to do it. Def factorial stream equals, oh, okay, this is factorial stream. There we go. Ready? Okay. Glad you're ready. I'll say stream dot from one. What is this? What does stream dot from one give? Oh,
Produce a stream.
Yeah.
1, 2.
Yeah. 1, 2, 3,
Yeah.
and so on. Okay. So I'm going to say this, and then I'm going to put in place. Okay. We could actually do some interesting stuff with zip. We're going to get to zip later. Okay. But something you could do here is to map, and actually, I'm wondering if this could be avoided. Give me a second here, because I'm wondering, can you do this? Can anyone check?
No.
Okay. Man. So we can map from an integer to an integer of long. Okay. And
But you can do something else. You can use iterate.
Yes.
And
Okay. Iterate would be another way. I'm going to do something a little bit like that. I'd be interested to talk about iterate. So what you could do is you could do scan 1L, and then this times this using the whale form. And basically this is, does anyone have a sense of what scan is going to do? It's like successively accumulating this. So the first is going to be 1. The second is going to be the first times the next. The third is going to be that last one times the next, etc. Okay. So here, and I'm going to say factorial stream succinct dot take of 5 dot force. Oh, okay. Mumble. Okay. There we go. Okay, now it started with there's a little bug here, but we're off by 1 there. But 1, 2, 6, 24, and taking some more of them. So it's actually starting from 0 factorial, 1 factorial, 2, 6, et cetera, 7, 20. So scan, let's explore scan a little bit, just so you can see what this does. This was the definition here. This bunch is just to convert it to a long, which is not nice. So you're saying you cannot do like from 1L, right? It'll be unhappy. Yeah.
Only accept integer.
It only accepts integers. Okay. Okay. So, ladies and gentlemen, let's just see how this scan works. It turns out scan is available for Scala collections. So I'll create a vector of something like 1, 2, 3, 4, 5. And I'm going to say scan, just so you could see how this works. I'm going to say scan of 1. And that's going to be used to determine the first element. And then the other, what am I doing? That was really interesting. There we go. If I did, so what you could see is these successive numbers come from where? Where does this one come from? Well, it turns out it comes from this guy. Where does this one come from? Turns out it comes from this guy times this one, right? Where does this next one come from? Well, it comes from this one times this one here. Okay. Sorry.
Times the output.
Yeah. Yes. You're correct. I mean, it's times the last one that was output. It's kind of a running total.
Yeah.
So another way to see this, it effectively is this one times that one. Yeah. But yes, that's true. It's a running total. Here we can do it with this. Do you see where this comes from? So here we're getting a running total here of the values, right? So this is just that guy. This 2 is from that guy plus this one here. This 4 is again, it's kind of the running total here. So it's those 2 plus this guy, and then the 7 is that last one plus corresponding one, etc. So this is basically a running total
of doing fold R on every subsequence of the.
Yes, I think that's basically a good way to do it. And so it allows you to accumulate along the way, or allows you to here multiply along the way, or allows you to, perform other operations along the way. I mean, this is going to be kind of an interesting one, but so you're successively doing, as Dorian says, you're successively doing for larger and larger sort of subsets of this. You're taking operations here, and this 0, for example, is going to be coming from the, I believe, the 1 minus this 1, and then that's going to yield 0, and so minus 2 from that, and then minus 3 from that, and then minus 4 from that, and then minus 5 from that. Yeah. Okay. So scan allows you to perform operations on a successively larger sort of set of the prefix associated with this collection. So you can accumulate or multiply or what have you. And by the same token, here we go. And there we are, right? Here we are with sort of factorials. Yeah, it's successively applying this operation based on some base 1. It's applying this operation to successive prefixes of this, right? Yeah.
So does that parameter to scan, does that indicate the index where it starts or?
No, it's actually, so if I were to do this, it will become clearer here.
Okay.
It's actually the starting sort of seed. If I were to do 2 here, then we start with 2, and then it's going to be 2 times 1, which is going to be a 2, and that accumulated values can be multiplied by this 2 to yield a 4, which is going to be multiplied by this 3 to yield a 12. You see that?
Yeah.
Yeah. Alternatively, if this were -1, then we're going to have it's -1 times this is just the first, this guy here, and then this one is from that one times this, and this next one is from this one times that one times that one. Da, da, da. That makes sense? Yeah. So it's almost like this guy is appended to this, and it starts with just that one, and then it goes successively. Yeah. Anyway, so that's another way to do fact, taking advantage of its built-in things. Okay. Great. So that was Factorial. I think what I'll do is I'm going to